Okay, the first physical law I want to talk about is Gauss's law for electrostatics, and this is of the form the charge enclosed by some region, and it's the total charge. It's equal to the surface integral of that region of the electric field. So remember, ds is just a shorthand notation for n.ds. So the alignment of the electric field with the normal vector, that is playing the role of the electric flux. And that tells you whether the field lines of the electric field are pointing sufficiently out of the surface. And if that happens, that what this formula is saying is that there's a lot of charge inside the surface. And it's worth noting that pluses and minuses cancel. So for example, the charge enclosed by this box is 0. And this would correspond to cancellation of those electric fields. Because remember, electric fields for negative charges, they point towards the charge. Electric fields flow away from positive charges. This is something you see in elementary physics classes. So this law is actually equivalent to Coulomb's law, but let me just try to motivate where it comes from. Well, it comes from experiments, obviously, but can we see this from a mathematical point of view? So it's worth asking, why is it a surface integral? And 2, why does the electric field show up? Why is this thing the integrand? Why is there a relationship between it and charge? Well, for the surface integral question, here's my take on it. This has to hold in every situation. So I could put any point charge and just at any point, I could move it to any other spot, and notice that in both configurations, the total charge is the same. So Q1 equals Q2. So it's unchanged by, let's say, by inside. It's unchanged by moving the charges. Okay? And so what that means is that the inside environment is completely irrelevant. It is completely irrelevant, and so therefore, all the action is at the surface. So therefore, the charge should be some surface integral. And there's going to be some integrand. So that's pretty hand wavy, but I think it can be mathematically rigorized, but we're not going to go there. I hope this is just good intuition, though. That you can see that the inside environment is completely irrelevant to the charge, so the total charge. So let me just talk about now why the electric field shows up, and this is I'm going to do on a dimension ground. So remember Q, we showed that it's equal to a surface integral of some integrand. So roughly speaking, on dimension grounds, F is Q divided by S. So it's charge divided by length squared. So now I'm just going to bring back up the electric field that we know from elementary physics, and it's some constant times our charge divided by r squared. Okay? So this is exactly what we have here, charge divided by r squared. Okay? So in other words, our integrand is actually equal to the electric field divided by that constant. And there's going to be some proportionality here. Okay? So that means we've showed that Q is some C over K. C is going to be 4 pi. Don't worry about it. Times the integral. Oh, what I mean by C is that there's no units. So for example, square root of 3. That's a perfectly fine C. It's not relevant. So now we have E ds. And so now we need a dot product. We need to change this to E dot ds vector, because the charge is a scalar. Okay? And finally, let me just note that K is 1 over 4 pi epsilon naught, where this is the permittivity constant. It's not, for this class, we don't need to care about what epsilon naught is. We'll just leave it symbolically, but physicists call this the permittivity constant. So if I plug this in here, our C over K will now be 4 pi epsilon naught C. So if we just choose C equal 1 over 4 pi, that cancels. That's stupid constant. So we end up with Q divided by epsilon naught, that permittivity constant, that's that integral. So the constant, of course, is the least important part of the calculation, but on dimension grounds, we saw from Q over r squared, charge divided by surface, that we had to have the electric field just on dimension grounds. Okay. In the next video, I'll show that Gauss's law actually works. Thanks for watching.